In this video, I will explain the conditions for equilibrium of rigid bodies in two dimensions. There are three conditions for equilibrium of rigid bodies in two dimensions. That the first condition is sum of forces in x direction should be equal to 0. The second condition is that the sum of forces in the y direction should also be equal to 0. And the third is the sum of all the moments above any arbitrary point O should also be equal to 0. So consider a body like shown in this figure. There are four forces acting on this body, and their sum of forces in x direction and y direction should be 0, and the moment produced due to these four forces should also be equal to 0. Then this body, we can say that it is in the equilibrium. So next we will do an example to further clarify our concept. So in this example, he is asking you to determine the horizontal and vertical components of reactions on the beam caused by the pin at B. You can see here there is a pin connection at point B and the rocker at A. So you can see here at A point the support is rocker support. You can see it's a roller beneath its rocker support, and is then telling you to neglect the weight of the beam. So this is our problem in which a force of 600 Newton is acting at this point at 45-degree angle. First, we have to draw its free body diagram. So on this right side, this figure, which is figure B, we have drawn the free body diagram, and at this point we have resolved this 600 Newton force into its y component. This is 600 sine 45, and this is y component of this 600 Newton force, and this 600 cos 45 is x component of this 600 Newton force. This is x, this is y component, and this is x component. This force, the second force is 100 Newton, and then we will draw the reaction forces. As you can see, the action forces are downward, so the reaction force will be upward. There is one reaction at point A. This is because this rocker support does not restrict its motion in the x direction. It only uh, restrict the motion of this beam in the y direction. So beam can move in x direction, but it cannot move in y. This is not allowed, but this is allowed. So there is only one reaction at point A, whereas this spin reaction does not allow any x direction, or in it does not also allow any y motion of this beam. So there are two reaction forces at the point B, and there is also a action force of 200 Newton at point B. So now we will apply the conditions of equilibrium. The condition of equilibrium are sigma m is equal to 0. The second condition is sigma f x is equal to 0, and third condition is sigma f y is equal to 0. So we have three equations of equilibrium, and we have to find three unknowns that are ay, by, and bx. These are three unknowns, and we have three equations of equilibrium. So we can find these three unknowns with the help of these three equations. So we start with the moment equation, and we will take moment about that point at which there are maximum unknowns. We can see in this figure that at point B, the unknowns, there are two unknowns at point B. So if we take moment about point B, then all these two unknowns bx and by will be eliminated from the equation. So we are now taking moment about point B. So these two unknown forces bx and by are passing through point B, and they do not have any perpendicular distance, so they cannot produce any moment. So this is the reason why we have chosen point B, and we have taken moment about point B, so that these two unknowns are eliminated from the equations. So now we'll take moment, and first we start from here that A by force is producing moment in the clockwise direction. This moment, this force is multiplied by this perpendicular distance, which is 2 plus 3 plus 2, and which is A by multiplied by 7, and because it is rotating the beam in clockwise direction, so a negative sign is placed. Second force is 600 sine 45. This is in the downward direction, and it will rotate the beam in anti-clockwise direction, in this direction. So it has a perpendicular distance of 2 plus 3. So it will be a positive sign 600 sine 45 multiplied by 5. The next force is 600 cos 45. So it has a perpendicular distance of this distance. This is the perpendicular distance, which is equal to 0.2 meter. This is given here, 0.2 meter, and it will rotate the beam in the clockwise direction, in this direction. So it will also be with a negative sign, and 600 cos 45 multiplied by 0.2. Then the force at point D will rotate the beam in anti-clockwise direction, in this anti-clockwise direction, because it has a distance of 2 meter. So it will come 100 multiplied by 2, and then we will equate this equation equal to 0. From this equation we know that only there is one unknown, that is ay, and we will get the answer of ay, which is equal to 319 Newton. So we have our first answer. Then we will apply the second equilibrium equation, which is sum of forces along x is equal to 0. So now we will sum up the forces in x direction. So we can see here that this force 600 cos 45 is acting on the right side, and on the right side x is positive. You can see here, and we write the equation 600 cos 45 minus this bx is also in the x direction. There is no other force in the x direction, so bx is with a negative sign because it is its direction on the left side, whereas x is positive on the right side. So we will equate it equal to 0, and then we will get our answer of bx is equal to 424. Then we will apply the third equilibrium condition on this diagram, on this beam, and we will sum up the forces in y direction. So first one is ay minus 600 sine 45 minus 100, and then minus 200. This one force is also downward, and then plus by is equal to 0. We have already calculated ay, which is 319, and from here we can find out by is equal to 405 Newton. These are the three reaction forces. Ay is the reaction at A point, Bx and By